Welcome to this presentation on Event Driving Architecture or EDA. Today we will explore the key concepts, components and benefits of this powerful architectural pattern and understand how it supports scalable, flexible and real-time systems. Event-driven architecture is a system design approach where components communicate by producing and consuming events. These events represent state changes, user actions, or external triggers, enabling the system to react in real time. The main strength of EDA is its asynchronous nature, ensuring that components remain loosely coupled and independent. EDA has several key characteristics. Asynchronous communication. It allows components to function independently without blocking the flow of other tasks. Loose coupling. This reduces the dependencies between components, making it easier to scale and modify individual parts of the system. Real-time processing. EDA systems react to events as soon as they occur, making them ideal for applications requiring quick responses. Scalability and flexibility. As each component operates independently, it's easy to scale them as demand grows. EDA is widely used in various industries. For example, in e-commerce, events like order placements or payment completions trigger actions like inventory updates and shipping notifications. In financial services, real-time event processing enables fraud detection and transaction monitoring. IoT applications use EDA to handle data from sensors and devices, while social media platforms react to user activities like posting or event or commenting through notifications. Event-driven systems are built with three essential components. Event producers. These components generate or detect events like a user placing an order or a system encountering an error. Event consumer. These components listen for and process events. For instance, a payment service may process a payment once an order is detected. Event brokers. Brokers like Kafka or RabbitMQ distribute events from producers to consumers, enabling seamless communication between different components. Event producers are responsible for detecting or creating events. They could be triggered by system actions, user input, or external systems. For instance, in an e-commerce platform, the producer would generate an event when a customer places an order. This event then travels through the system for further processing. Event consumers are components that listen for and react to events. When an event occurs, such as an order being placed, the consumer processes the event by executing business logic. In our e-commerce example, the shipping service could consume the order placed event to initiate the shipping process for the customer's order. Event brokers are the middleman that manages the flow of events between producers and consumers. They ensure that events are delivered to the appropriate consumers and handle message persistence in case of failure. Popular event brokers include Kafka, RabbitMQ, and Amazon SQS, each offering different features for event routing and management. Event-driven architecture offers numerous benefits. Scalability. Each component can be scaled independently based on load. Decoupling. Components are less dependent on each other, making the system more flexible and maintainable. Real-time responsiveness. The system reacts to events as they happen, ideal for real-time applications. Resilience. Fault tolerance is enhanced since events can be stored and reprocessed if needed. Flexibility. The architecture allows the easy addition or removal of components without disrupting the system. However, does come with its challenges. The challenges include complexity. Designing and managing asynchronous communication can add complexity to the system. It also have challenges in debugging and monitoring. Identifying and troubleshooting issues can be difficult without proper tools. Latency is one of its challenges as event processing delays in event processing might impact time sensitive applications. Duplication, ensuring that events are processed exactly once and handling potential duplication adds complexity. Various tools and technologies supports EDA. Event brokers like Kafka, RabbitMQ, and Amazon SQS are essential for managing event flows. For frameworks, we have Spring Cloud Stream for Java-based systems and AWS Lambda for serverless event-driven applications. Additionally, Avro and protocol buffers are commonly used for defining event schemas, ensuring consistency across the system. Let's take a look at a real-life example, a food delivery application. The system consists of event producers such as the customer placing an order, events broker like Kafka, which routes the order event consumers such as the payment service processing payments, the restaurant service notifying the restaurant, and the delivery service assigning a delivery driver. These components work in sync, processing the event in real time to fulfill the customer's order. When implementing EDA, here are some best practices. Design for idempotency. Ensure events can be processed multiple times without unintended consequences. Use standard event structures. Use tools like Avro or protocol buffers to ensure uniformity in event format. Monitor and log events. Effective monitoring ensures smooth operation and helps troubleshoot issues when they arise. Handle failure gracefully. Use retries, dead letter queues, and other strategies to manage failed events without causing system breakdowns. In summary, event-driven architecture is a powerful approach that enhances scalability, flexibility, and responsiveness. By decoupling components, EDA allows for real-time processing, enabling applications to react immediately to state changes. While there are challenges, especially around complexity and event management, the following best practices can help build robust, maintainable, and scalable systems. Thank you for your attention. I would now like to open the floor for any questions or further discussion on event driven architecture.